All right, welcome to today's webinar. We're going to wait just a minute while we allow everyone's connections to complete, and then we'll get started. We have a great panel here for you today to answer your questions on why pit slope design matters. As we're waiting for others to join, please feel free to say hello to our panel in the chat, which is located on your Zoom control bar. So you click on chat, you can type in there, let us know where you're joining from today, and say hello to our wonderful panel, who I will introduce in just a moment. All right, I'm going to go ahead and get started with the introduction for this webinar. Welcome to everyone joining us today. This is our first webinar that corresponds with the newest GCE course, which is the Fundamentals of Open Pit Slope Design course. And the topic of today's webinar aligns with section 1 of the course, which focuses on the fundamentals of slope design. And specifically today, we'll be talking about why pit slope design matters. So keep that in mind when you are considering which questions you will be putting in for our panel today. We'll be talking about why pit slope design matters. So this is an Ask the Experts webinar, meaning I have a wonderful expert panel here for you today that are ready and willing to answer and discuss all of the questions. We will run for 1 hour for this webinar from 1 o'clock until 2 o'clock, and that is Arizona time. So this webinar and the Fundamentals of Open Pit Slope Design course are brought to you by the Geotechnical Center of Excellence at the University of Arizona, which is where I'm joining you from today. The GCE is an industry-funded and member-led center where we work to collaborate for geotechnical research and education purposes by working interdisciplinarily throughout the university and throughout industry. Our goal is to bridge gaps both within and between academia, industry, and fields of study. And if you're interested in learning more about the GCE, you can contact anyone on our team. We'd be happy to talk to you more. And of course, we need to thank our member companies. So the GCE is member funded and member led. And on this screen, you see all of our members. And without them, all of our work that we do for webinars such as these, courses, and our research projects would not be possible. So a big thank you to all of our members, as well as our senior advisors and our associate members. Thank you all very much for supporting the GCE and our work. And as I mentioned, the webinar topic today is based on section 1 of our newest course, which is Fundamentals of Open Pit Slope Design. This course released on October 22nd, and it releases on a rolling basis for 9 sections. So we're talking today about the first of 9. Currently, 3 of 9 are available on the course site, and it will run all the way through March with the releases, and then will remain open for a year. So it is still open to new registrations. If you're interested, you can scan the QR code here, or one of my team, I believe, will put something in the chat for you to click on, or just feel free to contact us, gce@arizona.edu for more information. And a thank you to the Large Open Pit Project, or the LOP, who supported the development of the new course by underwriting the project. And thank you, of course, to all of our panelists, advisors, and collaborators for our webinar today. And now I'll introduce who is here with me. So I am Jillian Noonan. I'm Senior R&D Engineer with the GCE, and I'll be your moderator today. Alongside me from the GCE, I have a great team joining to help support with the questions and the chat and the Q&A. I have Allison Brucey, who is the program coordinator for the GCE. Allison, thanks for helping out today.
Hi, Jill. Happy to be here. Thanks, everybody, for coming.
And James McNabb, Senior R&D Engineer for the GCE, who some of you may know from our other courses and webinars. James, thanks for being here today.
Hello, Jill. Thanks for being here, everybody.
And then we have Christian Ortman, who is computing sciences researcher for the GCE. Christian, thanks for helping out.
No problem, Jill. Hello, everyone. Thanks for joining us today.
And now it is my pleasure to introduce our expert panel who will be addressing and discussing your questions. We have Martin Robotham, who is Director and Chief Geotechnical Engineer with Robotham Consulting Services. And Martin is also one of the lead technical advisors that's overseeing the content for the course. Martin, thank you so much for being here today and for all of your contributions up until this point. We really appreciate it.
Hey, thanks a lot, Jill, and looking forward to all your questions, everyone.
Also with us on the panel is Scott Silwick. Scott is Vice President of Call and Nicholas, as well as one of our lead technical advisors. Scott, thank you so much for being here, and thank you for everything.
Yeah, thanks, Jill, for hosting. Happy to be here. Hi, everyone.
And I will mention as well before I introduce the rest of the panel that our third lead technical advisor, Karen Moffett, was unable to join us today, but she sends her regrets and hopefully will be present on future webinar for you to meet her. Also with us today is Julia Potter, who is the director for the Geotechnical Center of Excellence. Julia, thanks for being here.
Thanks, Jill. Hello, everybody. Thanks for being here. Looking forward to a great discussion.
And we're lucky to have Lauren Lorg with us today, who is principal consultant with Itasca. Lauren, thank you. And you are muted.
Sorry. Hi, everybody.
And Derek Martin is joining us, who is Professor Emeritus with the University of Alberta. Derek, glad to have you on our panel today.
Thanks, Jill, and looking forward to all the questions.
And finally, we have Mark Hawley. Mark Hawley is Executive Director and Chief Advisor for Geotechnical with Pateau Associates. Mark, great to have you here today on our panel. Thanks for joining.
Thanks very much. And on behalf of the LOP, I'd just like to welcome everybody to the course and hope to be able to answer your questions.
Thanks, Mark. All right, so a very impressive panel here today, a lot of expertise. So let's not waste any more time and let's get right into some questions. But first, I will give you some instructions on how to submit those questions as a participant of today's webinar. So first of all, just some housekeeping. You are muted and your video is off as this is a webinar. If you do have a question for our panel, you can enter it at any time throughout the webinar using the Q&A function, which is located on your Zoom control panel. So you click on the Q&A icon and you can there submit a question by typing it. You can view questions that others have submitted. You can vote for questions that you like with a thumbs up. And if there are many highly rated questions, we'll pull those to the top of the queue. And then just noting that this is a recorded webinar. So we'll post it both to the course site as well as to the GCE's YouTube page when it is completed. And also note that the views and opinions expressed by our panelists are their own and do not necessarily reflect those of the GCE. And the content today that we'll be reviewing is for educational purposes only. And if you have a site-specific need for professional advice, we suggest that you do seek that out additionally. So thanks everyone for joining us, and let's get started with our first question. All right, so the way this works is I'll read out each question and then I will open it up to the panel for discussion. So the first question came in from the course discussion board from Thomas. And Thomas asks, if a mining operation is able to forecast an upcoming slope failure, are mitigation measures often implemented to try and delay the failure? Or is the time to failure calculated and the pit simply cleared out beforehand? My initial thoughts are that for a small scale failure, not too much would be done to mitigate it, as the mine could likely manage the result. But for large wall scale failures, in the event you know they're coming, are measures input to delay or prevent them? If so, how is this achieved? Or, on the contrary, would anything be done to accelerate them to get it over with? So great question by Thomas. Thank you for the question. And I will go ahead and open up to the panel. Let's see if there's anyone that would like to start on this question. If not, I can assign. How about Martin? Thanks for volunteering, Martin.
Happy to have a go at the first one.
Great, thank you so much.
I think with most geotech questions, the answer is it depends. It really depends on the size of the failure, the rate it's moving, the location within the mine, and the risk that it poses to the operation. So I think key for me would be understanding the failure that you have coming at you, where it would be, and what the impact would be. So, and in terms of the last part of the question, would you try and accelerate it? I think a few of us were chatting the other day about instances where I've certainly had large blocks pushed on a wall that we wanted to move that posed a rock fall threat to a haul road, and we tried to move it by pushing water down the slope to try and release it and to make it move. We were successful in that instance. We've also tried firing projectiles at things, which was a lot of fun, but actually didn't work very well whatsoever. So I think I'd say it depends, and happy to pass the question over to other panelists.
I'll take a bit of a go at it too. So the problem with trying to induce a failure is that it's hard to predict the outcome, and we often get unanticipated consequences of that. Either it doesn't fail or it fails in a way that we hadn't anticipated. So it's sort of a bit of a last resort from my perspective. In most cases, if you have intelligence that shows a large scale instability or potential instability well beforehand, I think that you first of all have to start thinking about, what can I do to mitigate this? First of all, can I stop it? Maybe I can through offloading or buttressing, or maybe I can do some things to manage the impact and anticipate where the run out might be, try to lessen the impact. So certainly being able to forecast and see something coming is an advantage. It's not a disadvantage. And we don't just use it to get out of the way. I mean, that's sort of a last resort. But well, I would say if we have, a history that points to an impending instability, we often want to try and do something about it. We're engineers. We don't want to just sit back and be passive. We want to try to be proactive. So in my experience, doesn't always work, but it's certainly worth a try. And we use lots of different tools in our toolbox. That could be drainage, it could be offloading, it could be buttressing, it could be managing surface water. There's lots of tools in our toolbox that we would probably want to try before just sitting back and letting it happen.
Yeah, and as far as mitigation measures go, usually the first mitigation measure that a mine would implement is to stop mining in front of the failure in that particular pushback. Sometimes when the failure starts, it's not sure what the mechanism is or what's causing it. So at that point in time, usually we don't know if taking another bench below that will destabilize the mass further. So usually the first mitigation measure would be to stop mining, figure out what's going on. Another mitigation measure you might try right at the onset of failure before you know too much is to look at what other areas are we mining, what other pushbacks are we currently working in, because we might need to start stockpiling ore. If we think we're going to be losing potentially one pushback for a certain amount of time to a failure. So we may want to dig harder or softer on certain areas of the mine if we're now starting to see a failure develop in one of the areas that we're mining.
So there are some very rare cases where failures are beneficial. I know of 2 or 3 where the failure fragmented the ore and made the ore access a lot easier. Of course, the problem with that is it's uncontrolled. It's not engineered. We don't necessarily like that, but at least in the cases that I'm thinking about, it wasn't as bad as it could have been because there was some benefit to it.
I think also you have to be careful with small scale failures, because that's the definition of small scale. At least in the pits are typically a bench, but if they're a double bench, so often you will find equipment like a dozer or something that's cleaning the bench or something that's mining the bench will actually get partially buried, and the safety becomes the big issue. So the risk always have to be evaluated against the consequences, of course. And small scale failures can be detrimental to the operations just as the big ones can.
Thanks for everyone's input. Any final comments on this question?
Just one thing that I thought of that I'm not sure was mentioned yet is I think it also to a certain extent depends on where you're at in the mine plan too, how much risk you're willing to take and what your mitigations might be. So I think that's a consideration, do you have one bench left to mine before you've hit the toe of your projected ore, or do you have a longer ways to go? So that's just another thing to think about in terms of how you mitigate and to try and delay the failure. But I definitely agree with Mark that we typically would not sit back and just kind of let it happen unless it's a rare case, like Lauren said, sometimes it can be to our advantage.
And one other thing we might try to figure out about a new failure is try to determine what type of behavior it's exhibiting. And when I say behavior, what I'm saying is whether it's regressive, progressive, or steady state. So in other words, does the failure look like it's continually accelerating, or does it only accelerate in response to certain triggers, such as mining at the toe or rainfall, and then it tends to level off? Or is it a failure made of a softer material that just tends to slowly displace over time, but doesn't really show a regressive or progressive trend? Just because that's a big question to answer that will help you determine how you might manage a particular failure.
We also want to see what the deformation signature looks like, and can we compare that to previous instabilities so we can get some insight into what the behavior might be. Not always the same, but having deformation signatures to compare to historical instabilities is a really good thing.
And I'll
I
notice.
think just, sorry, go ahead, Julia.
I was just going to say real quick that if those words that they're using, like progressive and regressive and deformation signature, are new to you and you're not familiar with them, our slope performance monitoring course and the LOP's book cover those topics really well with the LOP's book with the same title. And there'll be a bit of that later on in the course as well. So
I was just going to add, Julia, the importance of monitoring. Obviously, once you've identified it, it's great, but do you understand it yet? So is there any additional information on monitoring you could apply to better understand the trends that Scott and Mark are referencing to help you with either your remediation or your appropriate response?
All right, thank you very much, your expert panel. Any final comments before I move on to the next question? All right, this question is a short question, but I think it is a good one to lead into from the discussion we just had. And based on the fact that we are talking about a slope design course. So to the panel, I'll just open this up to anyone who wants to jump in. Does no pit failures equal good design?
I can start with an anecdote, if you like. When I was a technical manager at Bingham Canyon many years ago, I had my first geotechnical review board come to town, and they had a look at my pit at the time, and there wasn't a single failure in sight. And they said, "Martin, what have you done?" Had a look at the pit, it all looked fantastic. So a year later, we had our second geotechnical review board, and they said, "What the hell did you do? You've got failures everywhere." I just said, the pit just got older and things just started falling down. I didn't do anything. But I guess to get back to the answer to the question is, well, some failures are accepted as part of our design. Typically on a bench scale, we have tolerances to what we will and won't accept. So we do accept failure in some instances. We never accept or never will accept a safety impact to our business and our people. But as we've already mentioned, some failures can occur, as Julia said. If it's that last bench and you don't lose anything in terms of your reserve for your future mining, it can be not much of a problem and you don't mind. And I think when I started in geotech many years ago now, people used to say, well, when you get that last teaspoon of ore out of the bottom of the pit and the wall comes down, that's the perfect design. But now with closure considerations in mind, that isn't the case. So no, we don't want zero failure. That could be a completely over-conservative design. But then again, we don't want large failure, which impacts our business and could hurt our people. So again, over to everybody else.
It depends on scale and impact to the operation. It's not a global scale that's going to shut down the operation or kill the mine. the same time, we don't want to have such a conservative design that we can't manage a 1 or 2 bench failure in an operational context. So I think you've got to find the right balance, and that's often hard to do because you want to minimize the amount of stripping and have as steep a possible slope as you can. At the same time, you need to find the right balance between acceptable instability and failure. And I think that's probably a good segue into that discussion of what is a failure. Is it something that causes a bench to deteriorate, but you can come and clean it up with a shovel and move on? Or is it a failure is the fundamental failure of the design, which creates a global instability that has severe economic impact? So I think as I said, I think it depends on scale and impact.
The simple answer probably is a good design is one that satisfies the design acceptance criteria, because different mine operators are going to have different acceptance criteria. I guess I'm not really aware of any mine that says they don't want any pit failures, because you probably would end up closing the mine. But the amount and size and so on are dictated by the design acceptance criteria. That's a measure of the risk tolerance that the mine is operating to.
Very good. And a great question. Any other final comments before I pull another?
Yeah, I'm curious to poll the panel. We're talking about balancing the risk here. So potentially looking at the net present value of a specific pit design, and then seeing what the probability of failure would be and what effect that has on the NPV. What's the typical range of probabilities of failure that you would say are normal for an open pit mine environment? And in my experience, I've seen probability of failures around 5 to 10% used at some properties. But I'm curious if you all have seen similar numbers, or if think those numbers are appropriate or not.
Again, I think it depends on the scale.
And this for a large scale failure.
Tolerance for global instability, provided you can manage the safety risk aspects, which has to come first. I've seen anywhere from 2 to 5% for a global instability probability of failure. Much more than 5% starts to make the finance guys nervous.
Yeah, I'd agree, Scott. I'm happier with lower figures than that. 5%, 1 in 20 chance of a global instability in my mine. There's a lot of uncomfortable people looking around it then. And again, maybe a little controversial, but I'm not the biggest fan in the world of probabilistic approaches to large, complex geological slope failures. Much as factor of safety isn't perfect either, I think it's good to run multiple methods to have a look at, to try and evaluate the risk, and as Mark says, what the impact to your business could be.
No, I agree with that, Martin. Probability of failure is not my favorite topic.
No. But it continues to rear its head. It was popular 30 years ago, and then it kind of waned, and now it's sort of coming back into popularity again. So there's reasons for that, and most of that relates to financial risk.
Yeah, and I agree with you guys. Most projects, probability of failure isn't being considered. Some it is, but I guess in my mind, for us to figure out how to do it right, we have to keep trying. If we don't try, we'll never figure it out how to do it right to make it a standard of design.
Yeah, there's an interesting pop-up on the chat about from William. Is the 1 in 20 of a failure over the lifetime of a pit? It's a fair question, William, and I think what we'd like to see, or certainly my suggestion would be, you'd run multiple analyses and approaches to look at an individual failure, what the impact might be to your business. And in terms of business risk, each business might have a different take. Certainly the thinking used to be large major companies were very risk averse and smaller companies more nimble and willing to take more risk. But it comes back to what will your business and company tolerate? 1 in 20 over the life of a mine? Depends on the life of your mine. If it's short life, you could have a real problem there.
William says, thank you. All right, I'm going to pull up another question now from our live group, which is from Andrew. And Andrew, we actually had your question in the queue from the discussion board. And I believe to me it seems to be the same, if not similar. So I'm going to go ahead and mark your questions, your series of questions there as answered, but please resubmit any clarifying question that you might have after we address this one from the discussion board. So panel, this question from Andrew is, I understand that analysis types and methods should be selected to capture the controlling mechanisms for a particular slope or site. However, for projects where the geotechnical model and understanding of slope response is limited and of low confidence, controlling mechanisms may be unknown. In information limited scenarios, and there are a few questions here. One, is there a possibility that predetermined controlling mechanisms cause true mechanisms to be overlooked? Is there a relatively unbiased and systematic way to identify controlling mechanisms in the early stages of a project? And then two, what if there are critical mechanisms that were not known at the time of analysis, such as, quote, the black clay layer in massive rock mass, example provided in the lecture? And what is considered reasonable due diligence in this case? So, a few questions there. And it is directed to the whole panel, so I will see if anyone would like to volunteer to take this on in any part or in full to start.
So I'll give it a start here. So if we have limited information, we always want to fall back on our understanding of the geology. Understanding the geology is critical. And before we start relying on models to tell us what's going on, we ought to be looking at the geology and conceptualizing what possible mechanisms might arise. So I think that the first thing to do is go back and look at the geology and try to conceptualize what the controlling mechanisms might be, and don't rely on a model to tell you that. The model should be used to help verify your conceptual models, perhaps change your way of thinking. If the model comes up with something different, then that's something that you need to be thinking about. But first step, go back to the geology, look at the geology, conceptualize the model.
Yeah, I'd agree, Mark, in terms of, geology is always the first pass for me, but this really reflects also on study level, at that order of magnitude or conceptual stage where you have nothing but a regional geology model and the identification of the possibility of an ore body. That's all you've really got. When I look at these things, if there is a deformation or if there is a slope you're looking at, you've got to have that concept of structural geology, materials, water, and stresses, and what could occur, and then basically build up your model on the basis of the data that you have. And if you still have a lot of possible unanswered hypotheses, you need more data before you can make a decision on what's actually going on in terms of that controlling mechanism. So you'll only know what you know at each study level, and certainly at the conceptual level, your risk limits are very broad. Your NPV, or net present value variability for that study, will be very broad. And only as you come down to pre-feasibility, feasibility, and operational will you narrow down those risks, I guess, reduce the likelihood of missing a major controlling mechanism before you go ahead with your mine design.
Yeah, I think Mark hit the nail on the head with the comment on the geology there. Just because at the early stages of a project, usually we don't have geotechnical domains quite yet because we may not have enough data. So what we would normally do is use the geologic domains, so the geology domains, collect some structural data for a hard rock mine anyways. And the unbiased and systematic way that we look at it is just plot the stereonets, right? Plot the stereonet for each geologic domain. Then you can go through that, review it with your pit design, and get the first initial look at what the controlling mechanisms might be.
So I agree with that. I trying to paraphrase a bit what Everett Hook told me one time, and and that is that all the problems we deal with in our business are data limited, information limited. There are always going to be more information we'd like to have. But what he said is, look, do the very best you can with the information you have in front of you. Realize that down the line you're going to know more, but you can't beat yourself up about things that you don't know at the time. You have to make a recommendation or give an answer, and I think that's good advice. We can't always wait to get everything nailed down the way we'd like to. You have to move on with the best information that you have and the best analysis and best understanding, and get on with it.
And make sure your design acceptance criteria factors in to your level of understanding.
Yep.
All right, thank you, panel. Thank you, Andrew, for the great question. Any final comments before we move to the next? All right. So we have another question based on Martin's presentation, which is from Module 1. So Martin, I'll first direct this question towards you. And we pulled a nice image from your presentation that may be useful in your explanation. So the question is, in Module 1, you talked about the economic considerations of slope steepening. So what are the main factors to consider when a mine is considering steepening slopes?
Thanks, Jill. Look, a really good question, and I must admit I really love this very simple image, which hopefully you can all see and can all understand. I think a lot of the main factors we've already touched upon. I guess, you need to understand the mechanisms you're designing against, and you need to understand the risks to the mine that you can and can't tolerate, which reflects back to Mark's comment around your design acceptance criteria. So the main thing is it's not just a geotechnical issue. Obviously, you want confidence in the ore body being there and the grades being there to grab when you actually do steepen your walls, and also the characteristics of the wall that you will be creating, which in this case would be a steeper wall. What are the structures? What are the material properties? What's the hydrogeology going to be? And also need to look at the consequence of possible failure of this steepened slope and how it could be accepted by your operation. So it's really a risk-reward equation that you're answering for yourselves. Panel, other thoughts?
Again, just to reinforce, the design acceptance criteria needs to be connected to your level of uncertainty. So if you have a very well-defined model with good understanding of the structure and the fabric and the global stability mechanisms, then you have the information needed to be able to evaluate what kind of steepening, how much, and what the potential risk of that is. But without that, you don't know. So you need to connect your design acceptance criteria to your level of understanding at all stages and really at all scales.
One other consideration when looking at a slope steepening evaluation like this is not just the economics of the increased ore, but what increased geotechnical efforts will be needed down the line at the mine. So in other words, to do the red design, will you need increased geotechnical staff? Will you need increased monitoring? Will you need more radars? Will you need more piezometers? I really like earlier that Derek mentioned that, a 100-meter double bench failure or a 30-meter double bench failure can be just as dangerous as a 200-meter failure. So in this example here, it's also interesting that the original mine design had single benching, but the red design has double benching, which brings in a whole nother, set of risks that would need to be evaluated when looking at something like this.
Slope steepening is never free.
Yeah.
Because an interesting question comes when you have very, very strong rock with very limited geological structure. I often find these a huge challenge because when you look at the rock mass, which has no major through-going structure, you've got a very strong wall which stands up vertically for possibly great heights. Then you're flipping things around to not having maybe a major global instability, but managing rockfall over double and triple benches with vertical faces. They're a challenge because the economics look very good, and obviously going to a very high vertical wall is fantastic economically, but the rockfall risk increases dramatically. So how do you then use either artificial support or very, very good operational practices to limit the likelihood of rockfall and impact to your business on these walls? Sometimes the worst conditions are easier to design than the very, very good conditions.
Yeah, I think, Martin, this is another one that your first answer that you gave early on, it depends. The main factors that are going to influence the ability to steepen slopes are very geologic and rock mass dependent, and they could change from site to site. I doubt if there is any one sort of main factor that's going to always be relevant.
All right, thank you, panel. I think our conversation might now lead well into this next question that came in about risk. So different companies have different approaches to risk. Does mining leadership need to be better informed as to the importance of slope failure? And this is addressed again to the whole panel. So do we have any volunteers to start off?
So I'll volunteer again. I'm probably getting had enough of me already, but one of the things that I try to impress upon the engineers who work with me and my clients is that there are two fundamental jobs of the geotechnical engineer on a mine site. The first one, I believe, is to keep everybody safe. And the second one is to educate the decision makers as to what the risks are, what the potential mitigation factors are, and what the overall risk level is, so that those decision makers can make informed decisions about risk and risk tolerance. So to me, I think the geotechnical engineer is one of his main jobs is education, and educating senior leadership as to what the risks are and what the mitigations are so they can make good decisions.
So, Mark, I want to follow on from that because I really like the one project that you and I were involved in, and your suggestion was get the person who has to own that risk into the pit to look at the critical area and sit with the geotechnical engineer and have the geotechnical engineer explain to him what the risks are and what the options are. Doing it in the office maybe is not the right place to have that conversation, but when you're sitting at the bottom of a slope and looking at it, I think there's a much better appreciation for what risk actually means.
I come back to a funny story there, Lauren, where I had a mine where we had one of our senior executives come to the mine to visit to understand what the team did. And the mine prepared a beautiful lookout right at the pit crest, looking over the whole pit area with a fantastic view. And we got the guy in the lovely car to the very cleaned area, got him out of the car, and he's chatting away. He said, "Oh, well, if you come over here, you can have a real good look at the pit." He said, "Oh, sorry, I don't do heights." So we couldn't even get him to the pit crest to look into the pit. But flipping back to the question, I guess the answer is a resounding yes. Mining leadership does need to be informed. And I guess a lot of members of the panel here sit on geotechnical review boards. And it's really important that those review boards get to present to the senior leadership so that leadership gets a good independent understanding of what's going on. And also the review boards, if you have any at your operations, can help distill your messages upwards and get listened to by your leadership to hopefully better understand the challenges that you all face and hopefully the support that you need to do your job properly.
And I'll just note, amazing answers. That anytime the GCE polls our stakeholder group or our member group about topics that, you know, the community would like us to tackle, communicating how to communicate geotechnical risk to senior leadership is always very popular. So I think the answer is indeed a resounding yes, and people struggle with how to do that. So I think just that anecdote that Lauren gave about Mark suggesting that you bring the senior leader out into the pit, et cetera, is really useful and worth spreading that around a bit and maybe discussing this topic a bit further outside of just this one question in this webinar. So great question, whoever submitted it.
And not just from the pit crest. Pit slopes always look better from the top down, and they look a lot steeper from the toe up. So get your MD or CEO or COO, get them down into the bottom of the pit, right at the bottom of the slope, and have them look up. And it gives you a very different perspective. So I think that's important. Pit crests are beautiful visitor lookouts. They're not very impactful, I don't think.
All right, we have a live question that if there aren't any further comments on this, I'm going to pull up that continues on with the topic of risk. Any final comments for this one here? All right, so this question came from Meg, who's in our live group today. So Meg is asking, do you think it is necessary to design to typical design acceptance criteria, for example, a minimum factor of safety, given the amount of uncertainty associated with pit slope design? Should risk tolerance and risk management capabilities, empirical knowledge and engineering judgment, and the type of failure mechanism, for example, a deformation versus collapse, carry more weight in design? And this is all, again, addressed to the panel. I will accept volunteers to jump in.
Well, we can't let Mark Hawley start again, so I'll have my turn before somebody else takes the next one. So I think, Meg, it's a good question. And I guess the challenge here is, what is a typical design acceptance criteria versus what is your design acceptance criteria? And when identifying that pass mark, whether it be a factor of safety or a strength reduction factor or a probability of failure, all those things you mentioned, risk tolerance, empirical knowledge, engineering, type of failure, confidence in your geological models, your hydro models, all have to come to play to basically be part of that design acceptance value that you choose. And reflecting back on the previous question, you might find your people with senior leadership accountability and financial accountability are pushing back on you to say, well, I need more value. You need to steepen the wall. You have to find that balance, and it's not easy. Some of the papers you will have seen, maybe the waste dumps book that Mark put out, and there's a few other papers out there, look at model confidence versus failure, impact, and consequence. So as a business, you have to choose where you sit on that matrix of values before you embark on a design. Others?
I guess the only problem we all face is that we can calculate a factor of safety, but you can't measure it. And you can only measure the performance of the wall. And if you're having to deal with minimum amount of disruptions to the mining operations, do you really care about the factor of safety as long as the performance and everything is safe, performance is acceptable, targets have been met? So do you really care what the factor of safety is? Recognizing that you all have to start from somewhere. At a green site, the factor of safety has to be done in the typical precautionary approach that we use in engineering. But once you move to operations, we measure deformations continuously. We measure pore pressures in some mines, not all of them. So, you know, the performance can be measured using the tools that we have to measure how the pit walls behave. There's certainly more and more effort being placed today on reconciliation. There's great software out there because you often see, or people will want to change a pit slope by 1 degree or 2 degrees. And there's lots of great agony that goes into coming up with that change. But if you can't deliver the slopes to plus or minus 2 degrees, why all the angst? Because that's what you've been doing over, the various pushbacks. So there's a lot of information that needs to be evaluated when you're looking at this whole business of the design acceptance criteria. And it's factor of safety is just one part of it, but it's the performance of how the pit walls have been developed, the mining rate, the deformation rates, how things settle down. Can you just mitigate it with a small buttress? All those things play into it, and I don't think the factor of safety is a governing thing, although we all like it because it's so simple. Doesn't mean it's right.
And I'll address just the very end of the question there, that should empirical knowledge, engineering judgment, and the type of failure mechanism carry more weight in design? I would argue that they already carry a very heavy weight in design, because when we perform our slope stability analysis to try and calculate our factor of safety, we have to make a lot of decisions along the way using the empirical knowledge and the engineering judgment. And that's just to decide, what are our critical failure mechanisms and what analysis tools should we use? So for any given slope, we might be analyzing 4 different things that could happen, 4 different types of failures. Each of those might have their own factor of safety value, but then the one that gets reported generally to the stakeholders would be the lowest one of the different mechanisms that are analyzed. So I mean, I would argue that we are considering all those things and giving them a pretty good weight in the design as things stand now.
Getting the mechanism right is so important, and I would argue that we don't get it right very often, particularly on a greenfields kind of assessment. And our fallback is always, okay, we've got a design going forward that's based on some kind of acceptance criteria, and now we're implementing that design, and inevitably we move towards an observational approach where we instrument, we monitor the deformation, we adjust the design, but we're probably never actually creating that same design and maintaining that same factor of safety that we had at the initial design. I mean, it really is just a place to start, I think. And once you get into operations, it's about, as Derek said, about performance. But you need to monitor it and monitor and understand the deformations and the performance of the slope. And it has to be a continuous feedback on that. I don't really put too much focus on factor of safety once I'm into an operating slope. I think it's more about, is the slope safe? Are we managing the rockfall rate? Are there deformations that we can explain that make sense in terms of the mechanism that we think is controlling the interramp and global stability? Those are questions that are always going on, and you're always adjusting your thinking based on the latest monitoring data or the history of the monitoring data.
There's an interesting question by Robert just popped up on the Q&A, saying, shouldn't design criteria shift based on the age of the pit remaining reserves, i.e. should the DAC change with time? And I guess there the answer would be yes, because you should be increasing your knowledge of the geology, the performance, as you've said, Mark, already, of your pit with time. But one interesting reflection recently on some projects was dumps and dump design. They may have been designed to a certain factor of safety, but at closure, environmental considerations require a higher factor of safety. It's very difficult when you've designed a dump to a 1.3 factor of safety, but at closure it needs to meet 1.5. There's no magical number you can give to add a certain proportion of design acceptance back into your design. So I guess key there is know what your requirements are in terms of your corporate factors of safety or design acceptance criteria, because those are the ones at the end of the day, and even at closure, you'll need to conform to.
Another reason too why you might choose to use a lower factor of safety threshold for your design is if you have calibration data already. So if you're working at an existing pit like you're describing here, and there have been slope failures that then you've performed back analysis on, and you have a decent confidence that you understand the mechanism and have a good predictive capability of what those shear strengths are, then in that case, since you have a higher confidence, you might also be able to use a lower factor of safety value.
Yeah, this is a question I struggle with, because I get the concept of lower confidence requiring a higher safety factor, but I think there has to be a limit to it, because I think you can, if you follow that kind of strictly, you get to a point where you might be throwing away a good deposit for maybe unintended reasons. So I get the logic, but I always worry that applying it too rigorously at the very beginning could get you into a bit of trouble. Particularly when I see high safety factors like 2 in particular, if you're following normal procedures, you're actually dealing with materials that may not even exist. And so I think it's sort of incumbent on us to kind of make sure that if we follow that logic, we don't go off the deep end on it.
I guess, Lauren, there we also have to realize that resources and reserves rely on individual competent person who, based on their experience and knowledge, signs off or doesn't on a resource reserve. And there's often a lot of computation and geostats behind that, which have the same poor confidence in the parameters used as we do in geotech. So we're using very specific data to chase an ill-defined target, often is the case. So as we said before, there's an it depends with each stage of what we do, from resource definition to reserve to slope design to water management and so on. So I guess the challenge for everybody on the call, that this is not an easy job, but God, it's a really interesting role.
What does a factor of safety of 2 or greater actually mean? It means probably that the mechanism is not credible. You're so far away from limiting equilibrium that what does it really mean?
Mhm.
Yeah, I had a interesting discussion with Pete Stacy on this at one time, and he had an idea that at the beginning, one of the things we really struggle with is structures, knowing where they are, what they're going to be, and so on. And he had a concept that you don't have the structures in there, but the rock mass itself has to support a fairly high safety factor, knowing that structures are going to come into this thing and start to move you towards less stability. And I don't remember what his number was or anything else, but the concept was kind of interesting, particularly in greenfield sites, where we just don't know where the structures are. Maybe having some sort of allowable rock mass strength safety factor is one way to look at it. It definitely depends on the geology and trying to piece it together as best you can. But that was an interesting sort of point of view, I thought.
Well, I mean, you bring up a good point in that you may be better off keeping your low factors of safety and degrading the rock strength to something that could represent the deposit. Because typically, certain classes of deposit have the similar modes of failure, alteration, products, and so forth. And bringing that into the equation, which is basically the geological model, and keeping the factor of safety in a range that we're typically used to dealing with, and then dialing down the strengths to reflect what we know about the deposit and the geology. might be the better approach.
I think one other thing too to point out about these really high factor safety values is that usually when you get a 2.0 factor of safety out of your analysis, in my experience, the shear surface looks pretty silly. Like it doesn't look very realistic. But at the
Agreed.
same time, the analysis is telling you, hey, it's really, really, really unlikely that this is going to happen. I mean, I wouldn't call it a failure mechanism. I'd call it the non-failure mechanism because the analysis is saying this is the lowest I could find, but this is not going to happen. Don't worry about it. So I don't worry too much if I get a 2.0 and see a weird shear surface because it's the analysis is telling me this is never going to happen.
It speaks to the credibility of the mechanism.
Yeah.
Great discussion. We just have a few minutes left in the webinar. Any final comments on this one? No. I'm just going to pull up one more very quick, very easy question, and I'm going to point this one at Scott. And the question is just why geotechnical model instead of geomechanical model? So I think this might be asking, is there a difference in those terms? In the course and in the LOP book, it is geotechnical model. So why geotechnical model instead of geomechanical model? And Scott, I'll direct that towards you.
Yeah, I wouldn't worry too much about the semantics of it. I think you could use either term, and I think people would probably know what you're talking about. If you wanted to get into the weeds about it, at least to me, geomechanical has more to do with like the mechanical response of a material, so a rock or a soil. So the geomechanical parameters would be like cohesion, friction, Young's modulus, Poisson's ratio, things like that. Whereas geotechnical encompasses kind of all the different suite of parameters that we use in our world. So that would include empirical parameters, you know, like GSI, or index parameters like unit weight. But I think if you use either term, I think everyone knows what you're talking about. So either would get a pass from me.
Thanks, Scott. Any other comments from Thiago? Lauren, I know you know a thing or two about modeling.
Well, yeah, I think it is semantics, and I think Scott's got it about right. Geomechanical, the name sort of implies mechanics and wouldn't necessarily involve hydrogeology, for example, whereas the geotechnical models to me seems to be broader in what you're considering. So I prefer the term geotechnical model, but I'm not gonna go to the mat for any of it.
Great, thanks, Lauren. Any final comments from our panel before I close out the webinar? All right, well, I just want to give a great big thank you to you all for being here today. What a fantastic panel you are, and we had some amazing discussions. We're just so glad that you were able to provide your time today for us and for all of our participants in this webinar live and in the course. So thank you so much for being here, panel, and thank you so much for being here, participants. Those of you who we did not get to your questions today, if you are a participant in the course, please go ahead and transfer that question over to the discussion board, and I'll make sure to get that answered by one of our presenters or expert panel. And others that are not in the course, perhaps bring your question back for one of our future webinars. This is the first in a series of webinars that will be associated with the course. And if you're interested in learning more about the course, here it is again. So either scan that QR code or send a message to gce@arizona.edu if you'd like to learn more. Great session today. Thank you so much, everyone. And we'll see you next time.